Hi, this is Bill Freeman. I want to give you a few slides before the tutorial panel on the visual physics tutorial. So I want to talk about two things. One is using imaging to look at physics, and the other is using physics to help with imaging, to help create images. So an example of using imaging to learn by physics is the motion magnification technique that I developed with Fredo Durand, Mickey Rubenstein, and Neil Wadala, and others. Here's the main idea. Microscopes and telescopes enlarge the sizes of structures that you can look at. And here what we want to do is make a microscope that will magnify the motions of structures. So here's an example. Here's a video that's playing of a baby, and oftentimes parents of perfectly healthy newborn babies ask, is the baby breathing? Because they might have shallow breathing. And here's a motion magnified video of a baby breathing, where you can see it's the same video as what we saw, but the motions have been magnified, not the sizes of the structures. And this lets you see aspects of the video that you couldn't see otherwise. So there are a lot of potential applications of this. Here's another one. This is a crane in the wind, and we know that structures like this actually move around, but it's kind of hard to see it from this video. But if we motion magnify it, then you can see the motion of the crane, and you can see the end of it really moves quite a bit. So how do we do this? We take the image and break it up into a steerable pyramid transform, where instead of representing the image as pixels, we represent it as a large collection of wavelets with both sine and cosine phases at a large set of different positions, orientations, and scales. And in that transformation domain, then we can just record the phase of each wavelet and see how the phase changes over time, which tells you about position, and just amplify those phase changes over time, and then collapse back down to the spatial domain to get the motion magnified video. So here's a picture of that. Here's on the left there is a steerable pyramid transform that we use for the input video. We extract the phase, analyze, and then modify the phase as a function of time, and then collapse back down to the reconstructed modified video at each frame. And we think you can use this for lots of things, and it has been used for lots of different applications. But just to highlight one, let's talk about physics. Here is a high-speed video of a PVC pipe viewed end on. So looking at a pipe like this, gets hit with a hammer. And now when something like that gets hit with a hammer, we know from our math classes what happens is it rings like a bell and vibrates at this linear combination of normal modes, each with its own characteristic shape and frequency of oscillation. And we can see that so we take this input video that we just saw and we motion magnify it to amplify different temporal frequencies. And we can, selecting for the different normal modes of oscillation of the pipe. And so you can see that the different modes oscillate different frequencies, and the decay of the high frequency happens faster than the low. So you can see all these things from the motion magnified video. Other applications in physics include looking at the transition to turbulence. So here's InSense making the transition from laminar flow to turbulent flow. And my fluid mechanics colleagues tell me there are these instabilities in the laminar flow called Tolmin-Schlichting waves, which get larger and larger, and then ultimately become very large at the transition to turbulence. So we can motion magnify this, but in the video it's hard to see. But if you freeze a frame, then you can see these waves of instability that are getting larger and larger as you move along the laminar flow, and then finally break up into the turbulent part of the flow. And there are many different applications for this. It's like a microscope that lets you see the tiny motions that otherwise you couldn't see. My sort of mantra is that large catastrophic motions start out as small, tiny motions, and so you want to see them as soon as you can. So these are pointers to the web pages and articles and videos. Again, this was a long-time collaboration with Fredo Durand and others, in particular, former graduate students, Mickey Rubenstein and Neil Wadwa. Okay, that's using imaging to look at physics. Now let's use physics to develop new imaging methods. This is part of a line of work on so-called accidental cameras that I've been working on with Antonio Torralba. And we developed a particular example of that we call a corner camera. And this was made with Fredo Durand, Mickey Rubenstein, Fredo Durand, Katie Bowman, Yi, Didier, Warnell, Torralba, and myself. So you can look out at the world, and we know that if you're so lucky as to find a pinhole, then you might find an accidental pinhole camera from the structures in the world. But there's an even simpler structure which occurs all the time, which is a vertical corner ending on a flat plane. So like that corner there that we see in the center of this picture. And that vertical structure generates all sorts of high frequencies in the imaging matrix that relates the brightnesses on the other side of the corner to what is projected on the ground plane. So here's what you can do. You can take a video of the ground, and these changes in brightnesses on the ground that are induced by someone walking around the corner are very low intensity, but they're measurable. So they're invisible to the eye. They're about 1 part in 1,000 variation in the luminance, but it's straightforward to pick that up with a conventional camera and process it to reveal a picture of what's on the other side of the wall. Now, because the edge has only 1 dimension of variation, it's a vertical structure with no change along the vertical. These images that we can reconstruct from this camera are 1-dimensional videos as a function of time. But let's see it in action. So here's Vicky and Katie Bowman moving around the corner. And meanwhile, the camera is just looking at the ground there at the bottom left, and it can't see them. You can see this is very unconstrained, non-laboratory setting, just an outdoor scene next to a street. And here is the world's most boring video. This is what the camera recorded during what we just saw. And again, there are imperceptible brightness changes going on in the video that we can't see. But if you take that part of the ground and multiply it by this matrix as a function of time, where yellow is positive and blue is negative, that performs an angular differentiation, which tells you what this angle could see that the other angle couldn't see, and that tells you what's going on right there. And that gives you a readout of a 1-dimensional readout of an image as a function of angle around the corner of what the reflected intensities are. And here's one of these read out videos. So space is horizontal, or angle is horizontal, and time is vertical. And you can see this trace of someone walking around the corner, made from looking at the ground that we just saw, which looks so boringly constant. Well, it wasn't constant, it was changing a little bit, and you could read out those changes and make a 1D video. What can you learn from 1D video? Well, not too much, but you can learn interesting things. You can count how many people are moving around there. How many are there? Well, there's 1 in this case. Where did they move quickly? Where did they move slowly? You can read that out from this trace. And here's another trace where there are 2 people moving, and you can see that trivially from the video. So this gives you a way to look around corners in outdoor public settings with consumer cameras. And so this might be useful for public safety or for other applications. So to recap, we talked about using video processing to reveal interesting physics, this motion microscope. And we also talked about using simple configurations in the real world and sort of standard physics of light transport to pull out novel, unexpected, accidental cameras. Thank you.